You are able to see the PowerPoint, right?
Yes, sir.
Okay. So anyway, so last class, if you remember, we started this one. Okay. So how do we find out the ages, that crater frequency distribution, and other things also? Okay. And then if you want a geological classification, the geological ages and others, this is the only way to do right now, you see, for all the planetary things. And now, as already I mentioned, this impact is like a fundamental thing in the formation of solar system or in the formation of planets and all other things itself. Okay. So this I showed you, like, there are varieties of ways, a crater counting techniques, we say. So you count the number of craters, and the craters will be of several sizes, say. And then, you handle this type of data itself. Okay, that's what we said in the last class. So there are various ways of presenting those results, like, cumulative distribution, as like last class we said, right? Like you decreasing order, you do CDF, PDF, histograms, class intervals, all those things can be done itself. Incremental, so many methods are there itself. Okay. And then, as already we said, right, most of the cases generally, the size of the craters, the diameter of the crater versus how many number are there, how many such type of numbers are there. So there is a power law distribution is there. You follow? So which means, if you go to any places, the number of small craters will be more than the number of large craters. Okay, so that is how this power law distribution comes into picture. And if it is B is 2, say, so generally, D will have, one crater will be there with diameter D. Then D by 2, say 4 will be there. Then D by 4 will be, it is like multiplication kind of thing. It happens. Okay. So this is what they say, a power law kind of distributions. So the craters also, they fit these type of power laws. Okay. Of course, we will see there are some more other wavy natures also will come later on. So this is what, generally they fit for this itself. And then, so the basic criteria say, so like if the crater, if there are more number of craters, definitely, this will be more. And then, just 1 second. So now, if you see these things, so if you plot, two lines basically, okay, that is one region versus other region, say. If a region has more number of craters, basically, okay, so what happens is this line will be more and this line will be small. So obviously you can relatively, like a stratigraphy, so relative ages, which is older, which is younger, we can easily identify from these type of graphs itself, okay. So this is the most, the important thing which we saw in the last class. So R plot, you can variety of plots are there. Okay. So the production population we said, and anyway, we will come back to this once again itself. And then what we said was, I have sent you that NASA's report itself in 1979, because they said that, they have given a systematic way, like, how to process the craters, impact craters, and then how to analyze the data, because data analysis means you see many people, if we give the same data, say, so 10 different groups, say, they may come up with 10 different answers itself. Okay. And the data, the way how you are plotting also influences. If you take more number of bins, you will get a different thing. If you get small bins, you will get a different thing. So what they did was they identified some standard ways, the methodologies, okay, how to plot the crater counting data itself. So this also I showed you in the last class, like how do they do, in descending order, if it is unbinned data, binned data, say, like a root 2, should be the bin size, so all those things have been set, and this report has circulated to all of you. Okay. So this thing came, and this is a recommendation, and I think, in that report, if you see, say, they have given an example also, like, this is some lunar mare region. So how they have chosen the bin diameter, you can see how they have represented the surface area and that data set B, and then how do we plot this R plot as well as the cumulative plot itself. So this is a standard technique, which you have to use, if you want to do any analyze the data, so you have to follow these steps basically, so that, all the things will be like whatever others also doing, so they also will follow the same. The technique is consistent to say, then we can get some meaningful results, from this data set. Now this is as simple as, like in earthquakes also, say, like in hazard or whatever, we also do the same thing. Okay. So like this, I'm showing you the epicenters basically of all the past earthquakes. Okay, in our India, say some 19,542 earthquakes are there. Okay, so you can say that these are also something like impact craters itself. So even in earthquakes, say small dots will be more, the big dots will be very few basically. Okay, like large magnitude earthquakes, 8 magnitude, 9 magnitude. So you may find hardly 1 or 2 or maybe 3 in 100 years time period, say. And if the small magnitudes will be say 10,000, 20,000 will be there. So here also the same power law works itself. So if you calculate, so here what we try to do is, we try to select magnitude, let us say 19,542 events are there total. Okay, so now how many earthquakes are more than, how many earthquakes of magnitude more than zero basically. Okay, that will be 19,542 only. And how many earthquakes of magnitude more than 0.1, 0.2, 0.3, 0.4, like 5, 5.1, like that we calculate, and then you divide by the time period, say. So you will plot this type of graph. Once again, the same, the power law itself. Okay, so same thing happens for craters also. So like if you imagine, say these are all the craters, okay, of different diameters on moon or whatever. So here also, so you have to count the number of craters. So how many craters are more than 8 kilometer diameter, 8.1 kilometer, 8.2 kilometer. You can start with 0 itself, and then you plan, then you divide by the area here, because these are all spatial things. You divide by the area, and then you plot as the diameter, so you will get that same the distribution itself. So the same concept, whatever we use in earthquakes, same thing we are using even in our crater counting. There's a crater counting algorithms also. Okay, so this is what I told you. Like you see, so generally, if you take 3 regions, say like this may be some near land, near side moon or far side moon. So you have 3 distributions like this basically. So now, which is the oldest one among these 3? Yeah. So the oldest, how do you identify? So as already I told you, right, our thumb rule is, so if there are more number of craters, say, that region is old or young?
Older.
So old this one. So old means its frequency should be high basically. Okay, so this should be like this. So this line will have very old region, and this is a young region. So this is your stratigraphy, the relative ages. So if you want to compare, the craters in India and craters somewhere place, so you count and then you plot them, and whichever is old or young, you can easily identify from these type of graphs itself. So this is the technique which we are going to use. So this crater counting, this SFD diagrams, they help you to identify the relative ages. Okay, be careful, relative ages, between those things. Like stratigraphy also, I told you, it gives you relative ages. The top one is young, younger kind, this kind of a thing. But absolute age, you have to do some carbon dating, and then you have to do the correlation. So these graphs will help you in identifying the relative ages of those regions itself. Okay. So now, so here, that's what we said. Okay, now here, of course, it looks very simple, but when you try to do it in practice, say you may not get these type of graphs at all. So there are some lot of difficulties are there. Suppose for ideal sites, say you expect these type of thing, but when you go into moon or any place, this one, you have a lot of problems will be there. So the main problems are, sometimes what happens is the impact velocities actually. See, suppose you may have a diameter, 5-kilometer diameter crater, say, and then you can have another crater with same 5-kilometer diameter. But one crater, what happens is the impact velocity. If the impact velocity is, if it is 17, say, then it may penetrate more region. The crater diameter may be more, but if the impact velocity is small, say, so because it's a very complicated things, it is not like as velocity increases, things will increase. It's not like a linear kind of a thing. So when the impact velocities are different, say, although the projectile may be same, you may get different crater diameters also. So sometimes, I showed you, right, yesterday, lunar crater, say. So the lunar crater was perfectly circular. Even the Ramgad crater also was perfectly circular, basically. But when we saw the Dhala crater, say, any of you remember Dhala crater? What did we say yesterday? Whether it was circular, Dhala?
Very uneven shape.
Very uneven shape. So the reason, of course, we don't know the exact reason, but one wild guess is maybe the 90 degrees impact, or maybe the velocity may be different. So this will have, so this is another big headache actually. Okay, so that crater diameter is how much, because it is not even a circle kind of a thing. So the average impact velocities, they play a major role itself. And then resurfacing processes, we say, like erosion or something, resurfacing kind of a things happens. So the lava flows or something gets spilled or something. So they shallow the curve itself. So the old craters, small things may get eroded away. So that also is a big problem. Then we have secondary craters also. Like last class I told you, right? Once when a crater is formed, say ejecta, the material will fly off, and these ejecta will create another small craters. You follow? So that is a secondary crater. So generally, when you count the number of craters, you count that secondary crater also, and then but the secondary crater is not the original crater. It has been formed. It is like it depends on the primary crater itself. So this also is the biggest headache in the crater counting algorithms. How do you identify secondary crater, or whether it is a primary crater or independent crater? So that is a big headache itself. Okay, and then of course the target properties. You see, sometimes if you are going on a planet, these things some type of the rocks, like some region you may have a, like I showed you, right, in our what is it, geological map of India. I showed you long back. See, if you see in South India, so you are having very hard rocks, Archean rocks or something I showed you. But when you go to Himalayas, so you will see different type of rocks itself. So although the projectile velocity, the projectile diameter, everything is same, so because the target material is different, then also the crater diameter will be different basically. Okay, so when the crater diameter difference, so when you do counting, you make a mistakes in this one. Then of course mapping and counting, this is also biggest headache actually. Like last time I told you, you cannot compare, like if you are looking for moons, like near side of the moon, you have seen so many lava flows and others. Okay, but if you see the lunar highlands, I showed you where large number of craters is there. So if you combine everything, you may get a wrong result. So generally, last time I told you have to do geologically, the region should be homogeneous only. Then only you will get the exact picture itself. But how do you identify the geological boundary? That itself is a biggest headache. So when you try to do this mathematically, it is fine. But when you try to implement and when you try to do in QGIS or the real data, so you have a lot of issues. So what happens is, so these curves, say, you may feel, some errors may crop up, and we may be doing some type of mistakes itself. Okay, so these are the challenges. Okay, but still they can be, you can get these numbers also, it works also, but these are the practical challenges which you have to face when you are doing things in the practice, or when the real data itself. Okay, and these are also some more problems, like a cookie cutting, they say. Okay, so you can see these are the two original craters. So two craters are there. Now after some point of a time, a new crater has formed here. So now what has happened, this big crater has formed in this region. So what has this happened? So this big one, what has it done? Now, originally there was two. Now one more crater has been formed actually due to impact. So what happened to this crater, this small crater initially, which was existing before, say? Now what has happened?
Disappeared.
It got
Disappeared due to
disappearment, it got eroded. So now when you, this is the figure you are seeing, say. Now when you look at this figure, say, what do you say? You will see that there is one big crater is there, and one small crater is there actually. But originally, there were two small craters, you followed, right? So now if you see these graphs, you will say the small crater is only one, but originally there was two was there, but this other one got eroded due to the main event. So now see this graph, if you try to plot the size frequency distribution, say, so the number of craters which are more than 1 kilometer diameter is 2 here. Now here what happens, number of craters which are more than 2 will be there, but here you are having another big one also. So then your size frequency distribution, say, so this error will slowly crop up your this one. Then sand blasting process, we say, like you can see here, there is one big the crater which has been formed here. Then after that, you are having so many small impacts happened in the same crater zone itself, and due to these impacts, say, so this is the final figure itself. You followed. So now here, what is your observation? Now, so this was the original figure. On it, to so many craters happened, and this is the one. Now what is the here? So what has happened?
The big crater has disappeared.
The big crater disappeared. So now when you do counting algorithms, the size frequency, Now, when you see here, a number of craters which have diameter more than 50 kilometer, is one basically originally. Now, when it comes to here, say the number of all are small craters itself, and then you may be doing mistakes in the the large diameter, the frequency of the large diameter craters. So this is what they call a sandblasting process. Then blanketing process is there. Like you can see here, two small craters are there. These are this one, this one. These are the original. Now suddenly a big crater has been formed nearby region. Okay, not on the top of them, in the nearby region. But the problem, what happened was, this whenever a crater happens, you will see a lot of ejecta blanket actually. Okay, so much of ejecta blanket happened. So finally, what happened is this small crater disappeared. This also the boundaries have been disappeared. So you follow, right? So now the size frequency distribution, say it is very difficult. How many craters are there, or how to find out the frequencies. So these are some of the problems which you see in practice. So one is the target material, impact velocity, resurface, secondary crater. This is also another headache. So this is also another headache when you try to do things in practice itself. Okay. So that's what we said. So anyway, these are some practical problems, but still we can find out this SFDs actually. Okay, the size frequency distribution. So anyway, this is SFD this itself, and as already I told you, that report, NASA's report, which I sent you yesterday, that you should use it basically. Okay, so you can use histograms or that wind data. In that report they have given, then log graphs. So all those things one can see. And as already I told you, one thumb rule is the power loss. Generally power loss comes here, and they say that NCM, this is proportional to some 4 to 1.5, like that it happens, and then incremental, differential, relative, all those things will come into picture itself. Okay, so of course the most important thing, what thing is, whenever you see any region, say generally in moon or any planet, small craters will be more than the large craters, and the exponential, that is how this power law comes into picture. Not only the craters is one thing, okay, but the projectiles or the asteroids which had created that craters, you can, because both of them are interconnected. If the asteroids which are present in the solar system, say they only are doing the impacts, they only are creating the craters. So if you can study about the craters, not only you will know the geological ages, but you also can make some comments on how many asteroids are there in solar system, what are the sizes of those asteroids also. And then if you see in solar system also, say there is a we have a nice relation, like number of small craters are more than number of large craters. Similarly, if you see the asteroids in our solar system, say the large asteroids are very few, but small asteroids are so many actually. Okay, because both of them are interconnected among each other itself. So now here the most important thing, before anyway we go into the crater distribution and other things, one also should know how these craters are getting formed, or what are the projectiles, or what are the asteroids, or what are the things which are creating these craters actually. So that is very important. So one should understand, because both of them are interconnected. So what are those celestial bodies, you see, what are those asteroids or something, from where they are coming, which are creating the impacts on all the planets also. Because the size frequency distribution of impacts, the size frequency distribution of these asteroids and projectiles, both of them are interconnected to each other itself. Okay, so generally the main where these asteroids are coming up. Okay, not only it is very important for anyway ages itself, but somebody asks you a question on our earth also, in next 100 years, whether we will see any asteroid impact, because these questions are also very important to follow. So very important whether impact will happen on earth, then where it will impact, what will be its effect, and then these are very serious issues. Okay, and even on earth also so many impacts have occurred. See, Ramgad crater or lunar crater, Dalo crater, so they were formed some 50,000 years or more than that. Now we don't know, in the next 100 years or next 1,000 years, whether such type of things happens, what will be the, that is very important, the probabilities and others. Okay, so anyway, the size frequency, both of them are interconnected. So generally all these asteroids are the projectiles which are going to give impacts on the planets. They come from basically three zones actually. One is asteroids evolved from main belt orbits, like I showed you, right? Where is asteroid belt? Now, any of you remember where most of the asteroids are located in our solar system?
Between Mars and Jupiter.
Between Mars and Jupiter. Okay, excellent. That is main belt orbit. Then we have Jupiter family comets, they say. They come from trans-Neptunian region. I showed you long back, in our inventory. Cooper belt or something. So from there also these type of comets come and they create impacts also. Then there are some more comets are there. There's a long period comets. I think they are far away, or they may appear once or something like that. They may also cause the impacts itself. And there are also some more things like Trojan asteroids. Like they occupy Lagrange points. Any of you have an idea about Lagrange point? Recently, this word became very popular, Lagrange point. What do you mean by Lagrange point? Any of you have heard? Recently, that James Webb telescope went, right, where it is sitting. So the US has launched, right, James Webb telescope and others. So I think they have placed in Lagrange point, I think. So what do you mean by Lagrange point? No. You are listening this for the first time? No. So generally Lagrange point means, see, like for example, say Earth and Sun's gravitational forces will be there. So this is a point, say, where the gravitational pull, is, I think the centripetal force, you call it, it gets compensated, and the spacecraft, with less fuel, it can happily sit there. You followed. Otherwise, if it is some other place, say, it has to escape the gravity. So to escape the gravity of a planet, it has to burn some fuel and go to some other trajectory. So Lagrange point means, a minimum fuel, they say, where the centripetal force, gravitation, they get balanced. That is the main reason. So now in this Lagrange point, so many will be there, like from Jupiter to Earth, so many things will be there. There also we have this Trojan asteroids. Okay, they will be sitting there, and Halley type comets, it's a long period. So they also have this one, but they are not so much important for our planets. Now all these things is so they have their own probability. So main belt orbits, they have their own probabilities of collision, because of the orbits and other things also. Then Jupiter family will have different type of distributions, and LP has a different type of distributions, the collision dynamics. Okay, so both of them are very closely related. Our crater counting and then is a projectile sizes. Both of them are interconnected with each other itself. So anyway, so now the advantage is when you study the impact craters, you can also comment on these projectiles also. How many projectiles were there in the solar system long back. Now how many are there. So after 50,000 years, whether all asteroids are gone, through impact or something like that. So these questions also can be addressed by this impact, these craters itself. So Mercury, Venus, Earth, Moon, Mars, Martian satellites, a few asteroids, a couple of comets. So people have taken photographs, and these type of graphs have been plotted, and all these things are there. And then the relative ages of planetary surfaces may be estimated by counting the number of accumulated. This anyway is straightforward. So young surface, there is a fine. Now absolute interplanetary datings is a possible. Now if I know this for one planet, say, okay, so I can even easily, if I can get these type of things for moon, say, I can translate this for other planets also. Okay, I will show you at a later stage. So one was the bombardment flux, that is impact cratering rate, then impact conditions, scaling laws are there. We can easily, like the same thing happens on moons, how much, frequency will be there on Earth. We can easily translate among one another also. So that these are very, so that's why, that is the advantage of this impact crater counting algorithms also. Then astronomy, they have done, like you see the collision dynamics. Okay, so they do how many, what's the probabilities and other things also have done. So like, so this person, he demonstrated some main belt asteroids, they have initial orbits, more than 24 AU. Okay, I showed you AU last long back. Okay, that is the distance between Sun and Earth itself. Okay, so they are the most probable source of planetary crossers, and they're responsible for more than 90% of impact craters now visible on terrestrial planets. So these main belt asteroids, they are the number one. 90% is controlled by them itself. Okay, and of course LP comets is not very well not known because their periodicities are very huge. And Jupiter family comets, they are not numerous enough, the cratering rate of the terrestrial planets. So among these three, so the most thing comes from this asteroids. Okay, the main impact craters. Yeah. So generally what people do is they also plot size, frequency distributions of these asteroids and other things also. So nowadays the telescopes are there, so people have found out how many asteroids are there in our solar system, and they have also estimated the sizes of these asteroids and others. And then these type of graphs have been done, the size, frequency distribution for the asteroids, they have been plotted also. See, like near Earth asteroids. So this is your R plot for NEA. Then this is for I think some C-type asteroids, S-type asteroids. Say. So they have been found out also. And sometimes they have also compared this with the lunar craters. Say, like this curve basically. It is the impact curve which has been estimated for Moon. So this curve is same. So and this is the data of the asteroids. So it nicely, it matches basically like how many number of asteroids are there and how many impact craters are there on Moon. If you compare, say, then they nicely correlate with one another also. Okay. So now the another thing is impact rate estimates basically. Okay. So what is the impact rate itself? Okay. So this solar planetary bodies this can be obtained by models and then the theoretical concepts or whatever. So what they say is for about 4 billion years, we have the crater frequencies you can use and you can estimate all those things. So there is one very important thing. What they say is a cratering rate actually they decreased by a factor of 100 between 3.9 and 3.3 billion years ago. So like impact rates when a planet was formed, the impact rate was huge actually. Then slowly the impact rate has decreased. So this is what they say as impact rate. Now what is the impact rate in future, whether the impacts, the frequency of impacts, say how it is decreasing. So that is also becomes very important itself. And then that also helps in dating of the surface features, the geological age of the planet surfaces also. Okay. So this is what they say. So the rarity that produces fragments. So there was some theory was there, like I told you in the long time back. They said that comets are responsible for impacts. So there was one famous paper, the Shoemaker. I think some the comet name also may be there on his name. So he was the one. He said that the if you see any crater say with a diameter more than 30 kilometers, so they say that this is basically caused by the comets itself, not by the asteroid. So some theories was there, but then slowly, after a lot of things got this one. So they say that the comet fractions say like in impact crater, the impact craters done by comets is almost 10% only. So the most responsible thing is asteroids itself. Okay, so this also is a very important. And they say that comets have no negligible role in this impact cratering process itself. Then impact probability. This is also a very important thing. What is the probability of impact? So this also people study where because it's very important for our Earth and other terrestrial planets also. So there are this also you can get from the crater counting algorithms itself. Okay. So this is some table, which has been prepared by from this MPC catalog. If you type it in Google, you will get this one. So like for Mercury, say, like how many, this is H greater than 17 means that's the size of the asteroid it says. So the average impact rate, say, on Earth it is 1.3. So 1.3 per kilometer square per year. Of course, and you have to multiply by 10 to the power of minus 15 actually. It's a very small thing, but this is a very important thing. Now on Moon it is a 0.78, Mars it is 3.8. Mars it is very slightly higher than other things also. Then average collision probability say per one body, planetary crosser, it is given in one per billion years kind of a thing. So Earth, so these estimates also they have calculated because they are also very important for asteroid impacts on on the planets itself. Okay, so these and of course the average impact velocity also. So like on Earth, the average impact velocity is 19.3 kilometer per second. But if you see on Mercury and Venus, it's extremely high actually. And then you can see a nice, this one. So as the planets are very close to the solar system, say, the impact velocities also will be extremely high. Okay, although the other things are fine, but velocities also are very high when you come closer to the sun itself. So anyway, so these are the most important thing, So when you study the crater counting algorithms, you will know the geological age. Plus, you also will know the the size frequency distribution of the asteroids or the projectiles which has hit the planet, and then you can have an understanding basically, like you see what is the size frequency distributions of asteroids which are currently existing in the solar system, and what was its distribution say in when the solar system formed, and then in future how where it is going to be. So this so this crater counting will help you in all those issues itself. So anyway, this I have showed you. So how do we get the size frequency distribution? Okay. So one is as already I told you. So this is one cumulative form. Okay. Like as already I told you, right? You count the number of craters more than 1 kilometer diameter, more than 2 kilometer, 3 kilometer like that. You just plot it actually. or you can do in a differential form also, like instead of the derivative you differentiate it and then you plot the differential form. Then logarithmic form is also there, you take log and then then that may give you a nice picture about this one. Or relative form also they say it is same as this one only, but just you multiply by d cube. So the R plot they say, because this is widely used for even asteroids and other projectiles also. So there are four ways you can plot it. And the same thing, whatever that NASA document shows, same thing I'm putting here itself. Okay. Yeah. So now here, so this was the first, the earliest thing. So for moons, so he was a person, Wopik actually. So using a telescope, in Mare Imbrium, that place, he identified the craters and then he counted the number of craters and then he plotted this data. You can see these black dots here. So from the telescopic observations, say, so he got all these data itself. And now anyway, now we have satellites and then people have gone there. So now if you see, if you fit a data and then it matches very nicely with the current data itself, and then if you try to plot a this power loss, okay, so this exponent that this almost around minus the 1.8 kind of a thing you have, and this is a diameter here, and this is number of craters divided by the area of that Mare Imbrium area itself, so per kilometer square itself. So this was one of the earliest graph which in 1960s it was plotted by this Opik. Okay. So now, so the advantage is, so the you have, as already I showed you, you can plot in cumulative, differential form, logarithmic form. So many variety of ways are there. So they have their own pros and cons. Like cumulative things means like this type of a graph actually. So these graphs, because cumulative is something like integral. Okay. So when you integrate some quantity, say definitely it will be smooth actually. Okay. So cumulative things will be, no irregularities will be there, deficiency, bin size, and all those problems will not be there. But only problem is if there is any error, say, because you are integrating, the error becomes very small actually. Okay, so this is the one thing. Now, when you do the derivatives, the derivative of this one, so generally derivatives are like high frequency, the small things will get amplified, and then of course that it gives a nice this one, but things becomes amplified and statistically less significance, those issues will be there. Other the log differential forms say it is something like it is a balance between the first and the second. So you have a differential form, but you are also doing a logarithm itself, So then so this gives a nice way. So which is best means we don't know. The pros and cons are there. So you have to plot from all the approaches and then you have to get this inferences itself. Okay. And of course, ideal case is is on a planetary surface that instantaneously begins to accumulate new craters and never gets modified. This is the the ideal situation. So if you do for this, you will get beautiful plots. But general, as already I told you, in reality, as already I showed you, right, the secondary crater and all the other problems will be there. So things are not that straightforward. So, and that is also several issues you followed, right? The long-term exposure, so many issues can happen actually. Okay. So, like you say, from the very beginning, say, the ongoing bombardment, you see, it would cover the entire surface, So generally, so that then any new craters formed would destroy the older craters. I already showed you, right? That cookie cutting and other things I told you. Then the aerial crater density, say, it also stops to grow. So after some point of time, reaching some maximum value, defining a state of the so-called saturation equilibrium, basically. Okay. So this also they say equilibrium state. So equilibrium means the aerial crater density, say, it stops basically. You will not see any increase in these values. So this they call as equilibrium. Like this region has achieved a equilibrium state or something like that. Okay. So this concepts, everything was introduced by this Gould. He's also from NASA. In 1970, he has done a lot of experiments in the lab, and then he gave all these concepts itself. Okay. So that's what. So now if the product this quantity, say, so this cumulative graph or whatever. So sometimes size frequency distribution we call, but in planetary geology, say, people call also this as a production function also. You follow. So these are word they use it. NPF they use, or NPF, it's like it's a production function kind of a thing they use. Okay. So so now they have studied, like you say, N is greater than 2, say. That means small craters tend to erase large craters, like the sand blast regime. So he has done experiments, this Gould, and then he gave something like the steep production functions is typical for lunar craters, smaller than you see 1.5 kilometers. That means The small craters, they erase the large crater. Then the sand blast regime, say, which I showed you, right? One big crater got disappeared due to small craters, say. So then they say, the limiting the slope for all slope indices n greater than 2. So there are some observations have already been, people have done, like what is the effect of sandblasting on this curve, what is the effect of cookie cutting on this curve also. So this informations also are there. So for shallow production functions, say, so then the main mechanism is episodic renovation of the area by the largest crater. Cookie cutting, say. So that means n will be less than 2, n is more than 2, what happens? So these things have been, right now, things have been understood basically. Okay. And so now the SFD, say, so cookie cutting in the primary production phase. So like this, so many things are there. Then in the heavily created lunar highlands, we will see these type of issues itself. Okay. So then high target temperature during the earliest bombardment. This is also another subsequent decay of the bombardment rates. So this also will influence your size frequency distribution itself. This is what they say, the lunar production function. So people have done analysis for moon. They have already studied. Moon is very well studied, among all the objects in our solar system. So the crater counting, say. So mean moon, the main test, so many papers you can see in JGR, materials and planetary science, so in other journals itself. Okay. So what they say is, moon was, but there was a, the problem initially, they said that craters can be formed due to volcanic activity also. Then crater also can be formed due to impact craters also. So what now people say is, the volcanic, initially everything was volcano only because the temperatures are very high. So morely 3 billion years ago, it was all volcanic activity. After 3 billion years ago, the volcanic activity, it stopped, and then rocks have formed, and then whatever craters you are seeing, say, so everything is coming from the impact actually. So that is our understanding. So in the last 3 billion years, the lunar surface has been modified by impact craters only. Before that, everything was volcanic kind of a thing. And then of course, people have gone, Apollo lunar space missions went, and they have brought, I think, rocks from the moon. In the lab, they have studied whether it's a volcano or impact, everything has been this one. And then the lunar rock samples, so they provided unique opportunity basically, okay, to correlate number of craters, so this is subject of impact cratering, say. So this subject itself evolved due to Apollo and then Luna space missions. If these missions were not there, say, our understanding of impact cratering, would have not become not even advanced itself. Okay, so the number of impacts. So this is what it happens. So this is what they say. So here, as already, of course, there's a size frequency distribution only, but in planetary geology, as already I told you, people will call this word as a production function. That is nothing but the same n is equal to a, d times minus b only, but we call them as a production function. That is a product. It is a producing the craters or whatever. So that's what they say, PF basically. Okay. So the production function, so it's basically nothing but the size frequency distribution only of the craters that would be observed at the once completely renovated planetary surface before the area was saturated with the impact craters. That is what you see the definition they give for production function only. Okay. And of course, saturation, equilibrium, I already told you, there is no growth or this one on the old planetary surfaces, say. Okay. So, you can observe these type of equilibriums itself. So generally on lunar, the mares, that is the lava flows, equilibrium states we observe for craters more than 200 to 300 meter in diameter. So 300 meter, 200 meter, if you see the craters, you can see when you plot them, you will understand that there is no growth or whatever, they have reached some type of equilibrium itself. So the production function, of course, it depends on the diameters and other things itself. So finally, so what one does is for lunar, say. So, so in the initial days, the lunar production functions or size frequency distribution, everything came from the telescopic observations, before the human missions or before the satellites and other things. So this graph I showed you, right, this OPIC 1960. So this person said these black dots, that is, they have he got it only from the telescopic observations. So no, nothing was there. And of course now, so observations, when you do the observations, say, so he was able to see, if you see here, say, so he was able to observe what was the diameter. He was able to observe the minimum diameter now from his telescope, say. Can you read here? This is a black dot. So the minimum diameter he was observed using a telescope at that time was, what was the diameter?
Around 1 kilometer.
1 kilometer basically. Okay, so he was unable to observe small craters because it is a telescope itself. Okay, but in those days itself, he did this wonderful work, this OP. Okay, yeah. So he was 5 to less than 10 kilometer in diameter. The craters have d to the power of -2. When he fitted, say, -2 something came. Then later on, of course, the spacecraft images and all those things, and we can observe the topography data, say, whatever I think you people would have downloaded. I think 10 meters, right, resolution, 10 meters or even 5-meter resolution data sets are available. So now when you have data at that small resolution, so you can easily count craters, very small craters also, so this was happened. So now, so initially power law was thought about it. So everybody thought that you can easily fit a power law, that is a b to the power of d to the power of minus b kind of a thing in a logarithmic scale. But then slowly, as more data came into picture, say, so then people said it is not simple power law. Something else also can fit this type of data itself. So anyway, so this is what this thing. And of course, not only here, people made observations on other planets also, asteroids, so many things itself. So so what happened was, so these are production functions, say. So on variety of terrestrial planets, if you see for moon, if you see for Mars or something, variety things, they came up basically. Okay. But then, then they started looking at a universal relation. Like you see, can I have a one type of equation, say, for where all the planets, universal kind of a thing. Maybe the coefficients you can estimate. So power law, initially people thought everything will be power law, but this power law was not fitted, to some regions, some other planets. Say it was not working. Then other type of production functions came into picture itself. So right now, in the crater counting, say, of course, these two have two very famous, SFDs are there. Okay, are the production functions actual. Okay, and of course, not all these have been derived and validated, perfectly established for Moon. But then they have translated this to other terrestrial planets also. One is Hartman production function, okay, HPF they say. So which was developed by this person Hartman. He's also, I think, from NASA, maybe some this one. Newcomb, he's also a NASA, I think, professor or something in NASA. So they developed these production functions actually. Okay, two things are widely used. So the Hartman production function is a piecewise linear. Okay, it is something like instead of fitting one straight line, say, you fit three straight lines kind of thing, whereas in Newcomb production function is you write in terms of polynomials itself. Okay, so two things which are widely used to fit this crater counting data itself. So this is what they say. So the cumulative crater frequency versus diameter, say. So Hartman function, so this is a dotted line basically, you can see here. And then Newcomb, so you can see the Newcomb thing is, if you compare these two, say, which is a more oscillatory. Now, so if you see Newcomb, say, what is the difference between these two? So the Newcomb's function, if you see, you can see here it is oscillating. It is something like a polynomial thing. He has fitted. But whereas Hartman, say, he fits some type of straight lines, piecewise straight lines kind of thing to the data. Okay. So there's HPF, that's a Hartman production function. Okay. So this is what he said, designate table of ND data. So he did it, I think, long back. He has done a lot of studies and other things also. And the most important thing was, as already I told you, right, initial stage when they tried to study the impact craters on moon, say. So there was a strong theory which said, all these things are volcanic craters; they are not impact craters. Okay. So then, then the other theories also came up. The geological history. Either maybe not be there. So this was a geological history. If you see, say, okay, I think one slide was there. So this is a geological history of moon basically. Okay, billion years before present. You can see up to 4.4 billion years. This range is there. Okay, or 4.6 billion years. So the whole moon of this is a core that is 1,000 kilometers has been plotted here. The depth here. So the full moon, say, basically it was all liquid magma, or the lavas was there. Now after 4.2 or 4 billion years, you followed, right? Then thick crust started forming actually here. So all the crust came up here, and then what has happened was, so volcanic activity, it has stopped actually. And then so the craters started coming. And of course, some craters, these basalt flows are these type of things, like you can see the multi-ring basins. So this was the first step actually. The multi-ring basins, I already told you, right? The Oriental Basin, the mantle gets uplifted and other things also. So what now it is very well established that is some around 4 billion years or whatever say. So whatever craters you are looking in moon, the volcanic activity has stopped, and all those the craters they come from the impact itself. So this was a very important the observation. That's what happened. So once this theory was established, so here is Hartman, then he developed this type of production functions also. So that's what they say. Volcanic activity has ended, recently in moon 1.5 billion years, and then the basalt flows is 3.4 the billion years after they brought the samples and other things. So they say that, so these are all basalt things which you see, in Mary, Imbrium and other things also. So that's what they said. So finally they say that the volcanic things are gone, and then the HPF, whatever the production, they are all, everything is due to the impacts itself. So this was a very important observation which leads to the this production functions of impacts and other things also. So this is what they say. So relative fractions covered with basalts, they have estimated the ages and other things also. Okay. Of course, we will come back to this figure after some point of a time. This is what the Hartmann's, the production function are nothing but size frequency distribution only. As already I told you, right? So he started with this √2 diameter. You remember that NASA's document also shows, your bin size should be √2. So that concept he took it, and then he has fitted a straight line. So 3 straight lines. So one straight line is from 0.3 to 1.41, say, one straight line. Then from 1.41 to 64, one straight line. Then greater than 64, another straight line. So it is something like, small craters, say, they behave different way. Then the medium craters, say, from 1.41 to 64, they behave in a different way. And the large craters are, there's more than 64 kilometers, they behave in a different way. So he plotted 3 straight lines kind of thing itself. So this is what they call as the Hartmann's, the production function. So this he developed for moon itself. So this is what the Hartmann's function. You can see here. So one straight line comes here. Okay. So one straight line comes here, and then you follow it. One more straight line here, and one more straight line comes into picture here. Just 1 second. So 3 straight lines, you see, they have fitted one here, one here, one here, basically. And of course, this is a data. I think he has fitted to, I think, some region maybe. Okay. Okay. So now the same plots, instead of looking it in a cumulative plot here, you can also look it in R plot also. R is nothing but the derivative, differentiating this itself only. So you can see, so this thing you cannot observe clearly in the cumulative plot one straight line. That is 1.412, sorry. 1.41, then 64 kilometers. So you can see 10, 20, 30, 40, 50, 60, 64 here. One more straight line comes, and then, so one more straight line here, one more straight line here. You can clearly see this in this type of plot itself. You can see here 64, one straight line. I think the 2 is, yes, Hartmann's in the incremental form, R plot, okay, power law representation. No, so dashed line corresponds to anyways the saturation function here. So you can see, so these are the 3 straight lines which he has fitted itself. Okay, so this is one thing. Then the same thing, so he also tried to do it for Mars also. Then one more important terminology I just missed here. So these type of production functions also they call the size frequency distribution. They use the word production function. Apart from that, say they also use this word called the isochrone. Actually, isochrone is also same, the number of craters per diameter itself. Okay, so both of them are same itself. So the isochrone, they use these type of words itself. So this for the Mars also, like 1 million years. So you can see as the age increases, say, so the more number of craters, so the Mars also he established, right? This Hartman production function itself. The other one is the Newcomb production function itself. So this is like this actually. He has just fitted a polynomial itself. Okay, some 11th degree polynomial he has fitted to the data. So n anyway is the your crater frequency, d is the diameter, and this is a polynomial basically. So this is what he fitted to the data, and these are the coefficients a0, a1, a2, a3, a4, and for all the polynomials. So he has done some a older one, like you say 1983 he fitted, then 2001 he fitted. He has just data is more, because the resolutions are more. Then application variability, say from 0.01 to 300 kilometers, this one. Then he has also founded for the R plot also. Okay, so this also he estimated all these coefficients itself. And then this is what he also plotted, like you see the crater production functions, say, okay, and Hartman production functions or whatever for this Nectaris superposed craters. Okay, the Nectaris regions, a mere Nectaris region. So this is the data basically. You can see here these dots are all the data itself, and this is a curve. You know, he has fitted that in Newcomb 1983. So it's a polynomial basically. And then same thing. So he has also fitted, you know, the some this is a type of this is a new one, just he has calibrated his things itself. So this is a one. And then for the same data set, this is a Hartman actually. So Hartman's thing, you know, we have a issues, right? The Hartman things means, you know, he goes only by the straight lines kind of thing itself. Okay, so this is how the equations looks like. And then this is R plot. R plot is nothing but the differential. See why the Hartman's things derivative will be. Yeah. So if you see this graph set, Hartman is a straight lines, okay. So its derivatives will be, you know, like discontinuity kind of thing. But since it is a polynomial, say, so the derivative of polynomial also will be, you know, very smooth kind of things you will have. So these are the R plot actually. And now here, can you see here? See Nectarian, you know, he has fitted this to the Nectarian, then Mendeleev crater, then Zond 8, this one, and then, you know, of course from the lunar highlands basically, and then Mendeleev crater, Nectarian crater, then the Oriental crater itself. So you can see these curves have been, you know, nicely, you see this Newcomb's theory say, it nicely fits because it's a polynomial, right? It fits obviously the data, you know, in very nice fashion itself. Now you can estimate the ages, which is old, which is young from this type of graphs itself. So anyway, this is more lunar, this one. Now what happens? So the advantage here is this production functions advantage. Now you can say, like you see, which is a more you know, young, which is old thing. You can easily make, you see, like this may be old, this may be young. You know, the Oriental thing may be young, Nectarian may be here, Mendeleev zone D8. So obviously you can the relative ages can be estimated. You know, which is younger one, which is the oldest one. You can easily estimate from this graphs itself. Okay, relative age only we can get it. Now, how do we estimate the absolute age is a biggest problem. So now in Apollo missions, okay, so all of you know the human missions, Apollo 11, Apollo 12. So what has happened was they brought samples basically, okay, the rocks from variety of places, you know, the landing sites are the Apollo landing sites. So they have bought like Apollo 11, say 58 samples, they have bought 21.6 kg of rocks have been bought there, and igneous metamorphic rocks. They have done all the, you know, the classifications. Apollo 12 brought 69 k, you know, 34 grams, 34 kgs of rock. 42, you can see huge rocks have been brought from missions. Of course, L16, L20, these are the lunar missions, not human mission. It went and then took the material and then it brought back to the Earth itself. Okay. So from all these samples, so people have done like igneous rocks. They have identified that classification, the volcanic rocks, everything has been like a basalt, everything has been nicely, they have identified all these numbers itself. Whatever the weight, then all those the details have automatically come here. And then they have done the stratigraphy also, you know, like based on the rocks also, say, okay, they have got this stratigraphy also. So they have estimated the, you know, the years itself, basically from the carbon dating. And then what they have done is, you know, the crater frequency, say, so they have linked it to the ages itself, basically. Okay. So like from these rocks, you know, where they have landed, we know their age by carbon dating, you have estimated, and then you link it to the crater frequency. So this they have nicely, you know, done. So Copernican system means, you know, the crater frequency, say, if it is, you know, for more than 1 kilometer diameter, Copernican system means, you know, for a mere, it should be less than 7.5 into 10 to the power of minus 4. If it's a crater region, so 1 into 10 to the power of minus 3. Then, you know, if it is a pre-Nectarian system, these things are not available because these are very old things itself for more than 20 kilometers. Say. So for the crater frequency, for the craters of diameter more than 20 kilometers, if it is 7, if it is less than 7 to the power of minus 5, that means it is a pre-Nectarian system. So like this, you know, they have got this, you know, the numbers itself. Okay. So this they have nicely, you know, formulated, and then, you know, so these are the basically things itself. So now the age versus n of 1 itself. Okay, so this also they have plotted here. So this is the same thing only I'm just showing here. So this is Newcomb's relation set. Okay, so what they have done is his equation is there, right? This one. So in this equation, say, so if I substitute, this A naught basically, what does this A naught tells you? You can see here, there is no diameter here basically, okay? So when this log 10 n will be same as A naught. So what should be the value of D, which makes log 10 n is A naught only, this entire thing vanishes.
So 1.
1. So log of, that means, what is the crater diameter?
1 kilometer.
1 kilometer. So if I substitute 1 kilometer, say, then this becomes a constant A naught. So what these people have done is this constant A naught, no, it is linked to the age actually. So they have linked it with the age of the, these rocks itself. They identified the absolute age. So this has been done here. So the age here, this is n of 1. So n of 1 means, so you substitute in Newcomb's production function 1, then it becomes A naught itself. Okay, so this is how it happens basically. So Nectaris Basin, say. So you can see the ages basically. Okay, so Nectaris Basin is around 4 billion years or whatever. And the recent ones are Tycho crater, Cone crater, North Ray crater. So they all are the very recent, the craters itself. So this they were able to link with n of 1 versus the age. So so basically your production function gives you only the relative ages. But to do the absolute ages, what they have done is from the rock samples, say, they have estimated the ages of the rocks, and then these two they have interlinked basically, like how much should be the crater frequency versus the age of the material. So that also they did. Then finally they found out that n of 1, so that means A naught is closely linked to the age itself, but it's a complicated, you can see the graph is something like this. So this Newcomb's production function says, so he fitted this type of equation actually, okay? So this is anyway n of 1 or whatever, you see the maximum observed crater density. So they have done like less than 1 kilometer, what happens? More than 20 kilometer, because I already told you, right? So some Nectaris regions and others, you may have to look for big craters. So if you want to go, the older craters, say, they would have got the small things, they would have got destroyed, but the large things only we may have, But in the recent ones, you may have small craters only. So because this is an issue, so they have done this type of, the studies, 1 kilometer, 20 kilometer kind of thing. So this Newcomb said, okay. So what he says is approximately linear growth of if this graph only, if you see, say, okay, the same graph only. Okay, you're now one graph if you see here. So it says is approximately linear growth. So with surface age up to 3 billion years itself. Then exponential increased cratering rate for the older surfaces. So that figure shows this one. And then, so that this period of recorded high impact rates on the young moon is often called the late heavy bombardment period itself. So you can see here where the bombardment is very high. When was the bombardment extremely high? So this is a crater frequency here versus age basically. Okay. So when the crater bombardment are huge craters, when they were there, where frequency was very more basically. Now recently or in the olden age times? Series.
Olden times.
So what does it tells you? So when moon was formed in the early stages, okay, when moon was in early stages, so at that time there was so much bombardment happened on moon actually. But now slowly, what has happened now? What is the bombardment rate now? See, you can see here, see when at 4 billion years, bombardment rate was more or less close to 1 or maybe 10 to the power of 0 or 4.5 say. 1 was the frequency, 1 per kilometer square. So it means in every kilometer, one crater you will see like that. That was a bombardment. Now, what is the bombardment rate? If you see the first graph, more than 1 kilometer, bombardment rate is how much? Can you read this here at 0? If you approximately come to here, what will be the value? See 10 to the power of minus 4 here, 10 to the power of minus 6 here. Somewhere it will be. See for 1 kilometer craters, what is the frequency? 10 to the power of?
-5.
10 to the power of minus. But at this, when the moon was formed, it was almost 1 actually. Okay. So people also try to find out actually, like you see, when the moon was formed, that's what they say. This LHB, I think, late heavy bombardment period, they say, that also people found out from this impact rating loss. And this is the equation, nice equation, this they have fitted basically. That is this equation only. This line you are seeing, right? So this equation, if you fit with the time set, you will get a complex plot like 5.44 into the power of minus 14. Exponential thing is there, linear also is there basically. Okay, so when t is very, very small, say, what happens? So which one controls when t is very, very small, say? Okay, so when t is very small, what happens to this exponential? When t is 0, what happens here? E to the power of 0. What will be e to the power of 0?
1.
So when this is 1, say 1 minus 1, 0. So your n of 1, say how it is going to vary with t? Linearly. So that means in the initial stages, when times are, of course, this is plotted in a reverse minus this one, but in initial it will be, you follow, right, linear kind of a thing. But as t increases, now what happens? Which one controls? As t becomes very, 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 very large, what happens? Which one controls? Linear,
so exponential variation.
Exponential thing. So exponential thing controls. That is how that graph has been, plotted basically. Okay. So one can also say, like you see, you can find out the late LHB, that's late, what is it? Late heavy bombardment period. Also, you can estimate from this graphs itself. Okay. So that's what. So finally, the conclusion was, this A naught actual. That is, when you take diameter 1, n of 1, so it is highly correlated with, your this crater age itself. That is 10 to the power of 8. Okay. So that's what this one. So when t is 0, say, then 8.38 into 10 to the power of minus 4. So this is our value, n of 1 basically. So anyway, so this equation is valid for 10 meter to 300 kilometer, and you can easily find out, and then you can do. Now, what you have to do? Now, as already I told you, your assignment is say, okay. Now, what is that you have to do? Like you want to find out a landing site. So let us on moon, you have selected Mare Imbrium or some area, say. What you have to do? You have to count the number of craters itself. Then once you have counted the number of craters, say, what is that you have to do? You have to fit this Newman's production function or whatever, say. Or you find out if you don't want to fit also, it is fine. You find out the n of 1, that is what is the frequency for 1 kilometer diameter from your graph, and then you plot on this graph, say. So if you are n of 1, it is 10 to the power of minus 4, say. So then you can easily find out the age of your, the absolute age of the crater itself. So if your n of 1 is very high, say, like 10 to the power of minus 2 is your n of 1, that region you have got. So you plot here and you do this one, so you can easily find out your 3.5. So this is the how we will find out in the geological age of a landing site. Okay, so these I hope all of you are clear with this one. See how to find out the geological age of a surface. Is it clear to all of you?
Yes, sir.
So if you have any doubts, you please ask me, because it's a very fundamental thing. So what you have to do, you count all the craters simply. How many craters are more than diameter 0, how many 0.1, 0.2, 0.2, like that, you get your that graph. Okay, law n is equal to a d to the power of minus b or something, that that graph you have to plot. From that graph, so you take n of 1. Okay, or this Newcomb's fit, you fit this to your data, and you find out a naught basically. Anyway, a naught is anyway your n of 1 only. If you know n of 1, so from this graph, you plot where is your n of 1, you have to check it actually, or this graph itself also, both are same only. So you plot n of 1 on this graph, and then you can easily find out the age of your geological, whether it is a young or old or whatever. So you can easily get from this graph itself. Okay. So this is how we find out the geological ages of a region on a planet. Okay. So this is how we try to do it. It's very simple but very powerful, and it works nicely in practice, and it has been nicely been calibrated to moon things itself. Okay. So now that's what they said. So I told you that I told you that this graph, the most important thing is we can even find out, say, like what was the bombardment in the in the olden days actually, when moon was formed, is how much was the bombardment, what was the impact flux basically, like you see how many, how much was the impacts happened, why it has decreased, all those things also one can comment from these type of graphs also. So that's what they say. So t, so that's what, so t less than 3 billion years say, okay, is believed to be mainly the flux of. So now this impacts, where are these projectiles coming from? I told you, right? See, one is impact craters, trying to find out age is one aspect, but another most important question which we have to answer is, bombardments are happening, but from where these projectiles are coming, from where these asteroids are coming and doing this bombardment, because that is also very important, aspect for our Earth and other planets also, because our survival is depending on this bombardments itself. So the natures of the ancient flux 3.3, of course, this graph is perfectly fine here, but less than 3.3 say, although then it is fine, but our confidence thinks there are a lot of deviations are still not much understood, but it is fine. Okay, so this little bit of slight uncertainty is there. So there are so many hypotheses has been come up actually. So they say that why late that bombardments, what is the reason for this actually? What is the reason for the heavy bombardment at the initial stage, and what is the why the initial bombardment was very much high in the initial stages? Okay, so the reason was you remember, right, in the first classes I told you how a planet forms. Any of you remember? No. See how a planet forms in the solar system. I showed you, right, how a solar system forms. The dense molecular clouds say, the star gets formed, and then how a planet forms. Any of you have an idea? So I told you in the starting slides, right, in the starting inventory, how a solar system forms, how a planet forms. No. See how a planet is formed. People have not seen this one. So the dense molecular cloud will be there, and then what happens? Initially, the star gets formed, and then all the dust say, what happens? One will collide with each other actually, and then they welded, they get nicely welding, and then the planet forms. Okay. So what they say is that later that bombardment, so why it was heavy was the remnants basically of the planetized. That means the small particles which are not incorporated into planets before their differentiation and crust formations. They may be there. That is the reason the particles which was unable to form a planet. Due to that, this bombardment was one was the reason. And then the flux of comets. Actually, there was a huge comet flow was there from Neptune, Uranus, at that formation of solar system, or the flux of asteroids from the ancient asteroid belt, due to the migration we followed, right? So due to that, maybe this bombardment was very high in the starting stages actually. Okay, so that's what we said. So the observed impact craters, whatever isochrones or production functions you have done, so these are highly linked to the late heavy bombardment projectiles also. So the asteroids population, if you see their size, frequency distribution, both of them have nice the connection between the one among each other itself. Okay. Yeah. So the impact craters on other terrestrial planets, I showed you for moon itself. Now what about the other planets, or even for Earth? See for our Earth, do you have this type of a graph for Earth? See, this type of a graph is available for Earth. See, for moon, I have showed you. For Earth, whether this type of graph is available, or can you draw this type of a graph for Earth?
No, sir.
Why?
So because of weathering and constant changes, we don't know what happened there.
Excellent. And you remember, right? Our knowledge is about our terrestrial planet is very limited. We know only for the last million years only. You remember that dinosaur something years only. You don't have any idea. You followed, right? We don't know our history of Earth itself. 80% history of Earth, we ourselves don't know. So this type of a graph, you can't draw for Earth actually. You don't know for Earth. But Earth also, it would have formed by the same procedure only. You followed. So now, how this type of a curve looks for Earth is a very interesting question. Whether I told you right in the starting that Professor James had lecture also. He told the planetary things is not only to understand other planets, but to understand our own planet itself. We follow. So that was a fundamental thing. Why this planetary subject evolved. Okay. So now if you try to see other terrestrial planets, say like for Mercury, Venus, Earth, and Mars. Of course, Earth we are very much interested itself. So what they say is, if you know for moon, say moon is perfect, because there is no atmosphere and everything is nicely preserved on moon. So what one does is, because for Venus and others, they have atmosphere. Mars also, there also you have all these kinds of headaches actually. Okay, and huge atmospheres you can't even observe. You remember long back itself, you have to use some radar and other things to do the topography data also. So what they do is, one uses the scaling laws actually. Okay, I showed you right last class. If the same impact happens on Earth and if the same impact happens on moon, say you should have a scaling law. So if you know the scaling law, say like you see, because I told you right, simple to complex, it's the gravity is different. So if you have a gravity scaling law, say, So if you know the scaling law, so if you know anything for moon, you can easily translate it to Earth or other planet itself. So using the scaling law, say, this graph, whatever I showed you for moon, it can easily be translated to other planets itself. Okay, so people have done that also. So this graph I already showed you the impact probability and others also previously itself. So using this one, so we can easily, so if you see this graph, like just in the previous class I've showed you, like you say, as we are very close to sun, actually, the impact velocities will be extremely high itself. That's a very important thing. Then the average asteroid impact probability is 0.2 to 4 billion years. Okay, so that means an asteroid should orbit around the sun 0.25 to 5 billion years at the currently observed orbit before impacting a target planet. So these are extremely small. You follow the probabilities of asteroid impacts right now, so it's very, very small itself. Okay, so this is, of course, is dynamically impossible, like planetary crossers, like right, sometimes some crosses our orbits, this one, so that is not possible basically, okay, to hit our this one. So and then the given asteroids, it has a much greater chance of hitting the sun or being ejected to the margin of a solar system than to experience a crater forming collision with a planet because of so many this one. But without a supply of new bodies, because all the asteroids in our solar system, they were exhausted in the initial stages itself with impact craters. Okay, now the population is decreasing. Now, if you don't have the new bodies, the population of planetary crossers would become extinct. This also they have said. So asteroids or whatever, so they may become extinct also after some point of time, because all of them will do cratering, and they may even extinct also. Okay, so that's what they say. So new asteroids must be delivered from the main belt into the planetary crossing orbits. So they have so many observations have been done on this data set itself. Okay, and then the average cratering, say, for projectiles of the same size per unit area, okay, differs for all terrestrial planets because their gravity is difference. Okay, like Mercury and Mars, if you compare, say, entirely different itself. So the most dramatic difference with Earth and Moon, you followed, right? There is 20 impact. So if you see Earth and Moon, so this graph, if you see, say, average, the impact rate or whatever, say 1.3, 0.78, and collision probability is also 3.4, 0.16. You followed. So these also some numbers are that you can see, you can understand these things in an interesting fashion. You can do several interpretations. And Mars has the most variable orbit basically. I think it has some eccentricity also is there, approaches the main belt, and it experiences frequent impacts. Mars will have frequent impact. That's what they say. So these are, and of course the average velocity set. So you can have 13 to 50 kilometer per second. You see, it happens. So these are the some of the frequencies basically of impact velocity for terrestrial planets. It is not like one number or something like 19.3 or something. It varies actually. Okay. So in Mercury, if you see, say, you can see this is a histogram. Our asteroid like orbits, say. Okay. So it is something like 10, 20 to 50 kilometer per second will be there. And even Earth, say, this is a histogram which has been given up actually. And of course Mars and these numbers are there. Variety, the numbers have been provided here also. Now for other planets, say, how this size frequency distribution looks like. So now photographs are there, right? The graphs are there. So you can find out for Mercury and then Venus, the crater counting, algorithms, and you can draw these type of graphs also for Mercury, Venus, and other planets itself. Okay. So anyway, I will stop here. We will continue in our next class. So if there are any questions, you can ask. If there are any questions, you can ask.